All right, section 7.2. Today we're going to take a look at operations on decimals. And we're talking about your standard operations, addition, subtraction, multiplication, and division. And we're going to see some throwbacks into section 6 and the connections back in there, much we saw, not section 6, but chapter 6. Much like we saw in 7.1 when we looked at how do we decide if a decimal is even terminating or not. Okay, so we're going to have some of that going on too. So our leading idea is the following. Working with decimals requires careful attention to place value and precision. Small changes can have a big impact on the final result. Similarly, faith in God calls for mindfulness and intentionality in our daily choices. Just as decimal operations depend on aligning values correctly, living by faith involves aligning our actions with deeper spiritual principles. In both cases, small, consistent steps, whether numerical or spiritual, lead to meaningful and lasting outcomes. Dear Heavenly Father, I thank you for this group of students. I thank you for the call that you've placed in their life, and I ask that you would help us as we are working in class today, that you would give me the right words to say and that you would allow the students to have the ability to hear what you have for them. We pray in Jesus' name. Amen. All right, so we are going to start with addition and subtraction. And what we're going to be doing, that you've seen before, of course, is that we're going to line up the decimal points and subtract as with whole numbers. So sometimes people say to subtract as normal or like normal. Well, what you mean is like you did when you didn't have decimals. I understand that, but what we're really saying is we're doing it the way that we did it with whole numbers. And so we're going to consider doing this with the decimals 4 and 33 hundredths plus 3 and 26 hundredths. And then we're going to talk about why does this work? Why does that actually the way that it's going to be? So if we're going to line these up and subtract them the way that this is describing, just a second, sorry. We're going to take our 4 and 33 hundredths, and we're going to take our 3 and our 26 hundredths. We're lining up where the decimal point lies, and then we're going to add the way that we would have with whole numbers, which means starting on the right-hand side. So 3 plus 6 is 9, thank you. 3 plus 2 is 5, fantastic. The decimal point drops down, and then 4 plus 3 is 7. And it feels very natural. It doesn't feel like we've done anything super exciting, right? But there is a reason why this actually works, and it goes back to what we did in fractions back in chapter 6. So this is what we're going to take a look at in this particular part. So when we have 4 and 33 hundredths, what we really have is we have 4, we have 3 in the tenths place, and we have 3 in the hundredths place, right? We talked about that notation last time. And when we have 3 and 26 hundredths, we have 3 wholes. We have 2 in the tenths place, so it's 2 tenths, and 6 in the hundredths place, so we have 6 over 100. Okay, all good so far? And then what we did back in chapter 6 is we looked for things that had common denominators and we pushed them together, like we added those pieces together first, right? So we would have taken like the 6 and the 3 here. We would have taken the 2 and the 3 here, right? And we would have combined those pieces, and I didn't do them, but the 4 and the 3 as well. So let's actually go. These numbers don't have any rounding to them, so we don't have to, not rounding, but like carrying or borrowing to them, so we don't have to worry about that. But the 4 plus 3 is the 7. And then these two that I've circled in purple, I have a 3 tenths and 2 tenths, so that's 5 tenths. And then the ones that are circled in green, the 3 and the 6, is 9 100ths. And then if we put that back into decimal form, we're going to have, my 4 is wrong. Sorry, that's supposed to say 7. We'll fix that. We put that back into decimal form, we have the 7 at the beginning, and then we have the 5 in the tenths place, and then the 9 in the hundredths place adding up. Okay, that's why it's working for us. Okay, that's what this process is doing. You can also understand it if you wish, and doing it with these in the hundredths place to start with. So you could take 33 in the 100ths place. We could talk about being 26 in the hundredths place. It's a little less friendly because you're talking about 2-digit addition instead of single-digit addition, but of course it would still work. All right, so here's an example of a problem using addition and subtraction. and or subtraction. So this one says a stock price dropped from $63.28 per share to $27.45. What was the loss on a single share of stock? So as we're taking a look at this, what operation are we going to be using? This one's subtraction. So it started out at 63.28, and we're subtracting off the 27.45. Notice I'm not doing this with the fractions. That was not the point of me showing you that, right? The point of me showing you that was to show you why it worked, and now we can use it. So we're going to subtract as with whole numbers. So we start on the right-hand side. The 8 minus 5, that works just fine. 8 minus 5 is 3. But we run into a problem in the tens place. We have 2 minus 4, and we can't do that, right? So what we need to do is what? Borrow. Or we see it used as the word regrouping more commonly now. Okay, so what we would literally do if we were dealing with money, because this is a money problem, is we would take one of these dollar bills, because that's what this column is, right? It's single dollar bills. And we'd take one of those dollar bills and we'd turn them into what? What's in the next column over? What coin is this column? Say it louder. They're dimes. Thank you so much. They're dimes, right? These are dimes. So we turn them into how many dimes? 10 dimes. Oh, you guys are killing me today. Whew. All right, it's 10 dimes. Yeah, we're going to turn them into 10 dimes. So when we're borrowing or we're regrouping, the reason, and a money example is a really good one to say that we're pulling them over in tens is because it's because it's our place value system, but because that's what we're doing physically, right? We would take a dollar bill and we turn them into 10 dimes. Well, there's already 2 dimes there. So when I take my 10 dimes and I add it to the 2 dimes, how many dimes is that going to be? 12 dimes. So you're welcome to just put a 1 right here. Some people like to do that. I tend to put the number on top completely, and that's another option. So we now have 12 minus 4. So what's 12 minus 4? There you go. So you had 12 dimes. You take away 4 dimes. Now you have 8 dimes. And the 3, well, it's not a 3 anymore because we took one of those dollar bills and we turned it into dimes. So how many dollar bills? I only have $2 bills right now. And I've got the same problem. I have $2 bills and I'm supposed to be taking away $7 bills. So I need to come over to this place value. What bill is this? Okay, it's $60, but it's a tens bill, right? It's the bill itself is a $10 bill. So I have 6 $10 bills. So I'm going to take one of those $10 bills and I'm going to break it down and I'm going to make it into 1. I'm going to take one of those bills. I'm going to make it into 10 $1 bills, right? So we're going to take this 6 and we're going to come over here and I'm now going to have not 2. Let me move this down a little bit so we have some more space. I'm not going to just have 2 $1 bills, but like the last problem, I'm going to have 12, or last part of the problem, 12 $1 bills. And if I take 12 $1 bills and I subtract off 7 bills, how many do I have? 5. But I don't have 6 $10 bills anymore. What do I have? I have 5. So I need to represent it that way. So I now only have 5 $10 bills. And if I have my 5 bills minus my 2, I end up with 3. So the answer with units, because this problem had units, is $35.83. Okay, does that make sense? It's really an exchange process, okay? And if you were doing this with a drawer of money, you guys would be really good at it. At least most people are pretty good at it because you've dealt with money. You guys probably aren't as good at it as people 10 years ago because you don't do dollar bills very much. We do this, we scan our phones or we scan our card, right? But still, a lot of people pay with dollar bills. And so this is a way of getting back to that idea of why we're borrowing 10 or we're regrouping with tens. Okay, let's do another operation. We're going to do multiplication. So addition and subtraction kind of get grouped together because they work the same way. Multiplication and division are going to be dealt with separately. So with multiplication, we're going to multiply as with whole numbers. Then count the number of places after the decimal point in all factors. And this will be the number of places after the decimal point in the product. And our example is 3/10 times 7/10. So what this is telling me is that I'm going to rather ignore the decimals for the first part. I'm going to think of this as 3 and 7. What's 3 times 7? 21. Okay? And then I'm going to count the number of places after decimal points. So I've got one place right here in my 3. And I've got one place right here in my 7. It's a total of 2 places, right? And then the decimal point that I will insert into my 21 has to have 2 numbers after the decimal point. So it goes right here. That's what the algorithm says to do. This will be my answer. I do feel like, especially with this one, maybe more than the last one, it's a little bit less clear as to why we're doing that. It looks a little bit more like magic. Or, like I told you that's how it's supposed to be and therefore you should believe me. But again, it actually goes right back to what we did with decimals. So how would I write 3/10 in decimal form? In fraction form, excuse me. 3/10. And how would I write 7/10 in fraction form? 7/10. And resist any urge. This one doesn't have this, but if one of these had been able to be simplified, like if it said 0.4 times 0.7 like that, you could simplify. We're not trying to simplify anything. That's not the goal. What would we do with our standard multiplication algorithm for fractions? Exactly. Go across the top, 21, go across the bottom, 100. And lo and behold, look at what that denominator says. It says 100. So what place value in decimal form should our decimal end in? The hundredths place, right? That's 2 locations after the decimal point. And sure enough, that's exactly what we got when we followed this algorithm. This is why it's working for us. There's nothing special with the 3/10 and the 7/10. It's just an example showing it. Okay? So let's look at division. Again, told you we were going to treat them a little bit separately. With division, it tells us that we're supposed to make the divisor a whole number by moving the decimal point in the divisor and dividend an equal number of times, then divide as with whole numbers. So let's actually look at what that's telling us. So when we write this out, the first number, which is 75 hundredths here, is going underneath the divisibility sign. The second number is our divisor, and it goes on the outside. We do need to make sure we get those in the right order. There was some swapping around of some of those kind of things on the test, okay? So what this says I need to do is I need the number on the outside to not have a decimal point in it. That's what it's actually telling you. So if I were to take the number on the outside and I were to move the decimal 1 location to the right, I would no longer have a decimal value on the outside, right? I'd just have a 5, correct? But it says if I move the decimal 1 out here, I need to move the decimal 1 inside as well. So the decimal moves here. I'm going to rewrite it just for clarity, not that you need to rewrite it when you're doing it, but this is where I am at this point. 5 on the outside, 7 and 5/10 on the inside. Okay, everybody good? And then it says we're going to divide as with whole numbers. So the decimal point that we see here is going to come straight up. That part's not as with whole numbers because we didn't have decimal points when we were working with whole numbers. But aside from that, this 5 goes into 7 how many times? Once. So we're going to put a 1 on top. 1 times 5 is 5. And then 7 minus 5 would be the 2. I don't need to worry about dropping down the decimal. That part's irrelevant to what I'm doing in the division piece. I just need to drop down the 5. And then 5 goes into 25 5 times. So 5 goes above the 5 on the top. 5 times 5 is 25. I've got a remainder of 0, which tells me then I'm going to stop. Okay? Now when we get to 7.3, we're going to see ones that don't stop. They never get to 0. We'll deal with those later. Okay, but that's not where we are just yet. Okay? So that looks really good. The answer then, this is my answer right here. The answer is 1.5. But again, there's got to be a reason why that works. Or it didn't just come out of nowhere. So I'd like to show you why that works from the standpoint again of fractions. Thank you so much. Yes, that's what we're doing. Okay, so it says that we have the 0.75, right, 75 hundredths on top, and we have our 5/10 on bottom. So this is what this division means in fraction form. Now there's other ways we could write it in fraction form, but this is what division means, not the decimals, but the division means in fraction form. So we learned that when we were working with fractions, as long as we multiply the top and the bottom by the same value, that the whole fraction itself does not change, because we're multiplying the fraction by the number 1, right? So we're going to do that here as well. We're going to multiply the top and the bottom by 10. 10's a really nice number to multiply by. And the reason is because the 10, when we multiply by it, just moves the decimal one place. That's what we did over here, right? Move the decimal point one place. So over here, we're going to be able to move this decimal point one place. So now I have 7 5/10 divided by 5. And now that I'm at this location, right, at this spot, right, I agree that there's still a decimal point in it, but the point being that the denominator doesn't have one. And I can actually see that exactly I would arrive at the same location that I did over here from that perspective. So when we're moving the decimal point in the divisor and in the dividend the same number of places, it's because they represent the numerator and the denominator of a fraction. That's why that's happening for us. Okay? So you're starting to feel about why we started with fractions before we did decimals? It all goes back to what we did in fractions, and that's why I told you when we're doing fractions, you can't do anything with decimals yet, right? Because this would be circular reasoning. We're not doing that. All right. Scientific notation. So a couple of things about scientific notation. So I suspect that at some point, if you haven't already, you will take some science classes here at OBU, perhaps with Dr. Marsh, as in Dr. Marsh, that's the man, right? Not the woman, Dr. Marsh. She might be your geometry teacher or number 3 teacher, but, or who else is teaching those classes right now? Does anybody have somebody else who's teaching one of those? Dr. Hofeld. Okay, so they rotate a little bit, but scientific notation shows up and it's used in very specific cases, not in everything. So if you want to tell me what your bank account is, you're not going to tell it to me in scientific notation. It wouldn't make any sense, right? But scientific notation is used for things that are either very, very large, like the distance from here to the sun, or something that's very, very small, like measuring the size of molecules or atoms or something like that, right? Something very tiny. Hence, that's why it's called scientific notation. These are science-related ideas, okay? So we're not using scientific notation for things that are just the things that we do in typical everyday life. We're using them for things that are very, very large or very, very small. And the basic form of this is that they're written in a times 10 to the n form, where there's some specific pieces of information about that a and n that matter. The a value needs to be between 1 and 10. And notice it can include a 1, right? That's the equals underneath, but it doesn't include a 10. In other words, it can't have more than one number before the decimal place. Okay, that's what that's telling you. And then the n value is an integer. And we talk about integers in number theory, but you've seen them before. Integers are positives and negatives that are whole values. So like -5 and +15, those are integers, but 5.7 is not. It's a decimal, right? We call it a rational number. So we're talking about whole numbers, no decimal places, no fractions, nothing creative, no square roots or pies or anything like that. Okay, none of that's happening in that exponent. So as we take a look at these, we want to be able to take a number that's in standard form, right, like your bank account number, the value in your bank account, and be able to put it into scientific notation and vice versa. Okay, we're not going to do that with your bank account number, but that's the idea. So standard notation is the notation that we use in most of our life. All right, that's what it is. And we want to be able to put it into scientific notation, and we want to be able to go the other direction too. So on this one, it tells us we're going to move the decimal point to create a value between 1 and 10. And we're going to count how many times we moved the decimal point. How many moves did we make? If the original number in standard notation is a large number, and by large I mean more than 10, okay, these are sort of, the words large and small are very subjective. So I'm giving you my subjectiveness to what this is. Large means more than 10. If it's more than 10, your exponent's going to be positive, and if it's less than 10, not less than 10, less than 1, right, your exponent's going to be negative. If it's already between 1 and 10, it's already in the a value you need. You didn't have to change anything, okay? So that's why it doesn't address that. Bigger than 10, positive. Smaller than 1, negative. So we're going to do an example. This number is 298,000. We're going to turn it into scientific notation. So step number 1, I'm just going to write it a little bit larger so that we can have more space. I need to insert a decimal point in the location where I create a number that's between 1 and 10. Where is my decimal place going to go? Yes, it's going to go in between the 2 and the 9. Okay, does that make sense to everybody? If I put it anywhere else, I will either create a value that's smaller than 1 or a value that's bigger than 10. This is our location. Now, it's probably worth noting that that's not where the decimal point started. Where did the decimal point start? Because it's not in that number. So where is it? Yeah, it's after the last zero that's there. So this is where it started originally. I'm going to do it in black, and we're going to move it over to the purple, okay? So it started where that end of the number ended, and we need to count how many places we moved it over. So this would be 1 place, 2, 3, 4, and 5. Notice I'm counting around each number. I'm not counting the number. Don't confuse the issue. We're going spaces. I've moved it a space where the decimal point lies. It lies between numbers. How many times did I move it? 5. Cool. All right, so we said that this number is 2.98 times 10, and the power is going to be 5. Is it going to be a positive 5 or a negative 5? Positive. How do we know it's positive? Because it was larger than 10. Large number positive, small number negative. Okay, does that make sense?
Would we put 2.98 or just 2?
I left it off. Thank you. I was so excited about my 5, I forgot my 8. Yes, 2.98 times 10 to the 5th. It could ask you a question to round that number sometimes too, where it wants a certain level of accuracy that might be the case, but this one did not. Thanks for catching that. Okay, is that all right? All right, I think we're moving to the next direction. Indeed. So now we're going the other direction, scientific to standard. So scientific to standard is we're going to move the decimal point. Again, we're moving decimal points. The number of places indicated by the exponent. If it's a positive exponent, the number gets larger. Okay? And if it's a negative exponent, the number gets smaller. I'm going to pause for a moment just to make note of the fact that not all resources teach it as positive larger, negative smaller. And there's a reason that I do. A lot of resources teach it positive, you move right or left, negative, you move right or left. The tricky thing about that is that you have to make sure which one you're starting with and which one you're going to, because it goes opposite directions depending on the positive or negativeness of it, depending on which way you're going. And if I present it and think about it like this, I don't have to think, which direction am I going? Positive always means large. I don't have to think, positive means left or right. Which direction am I going? Are you with me? Positive means large, and negative means small. So we're going to take our value that we're given, that's already in a scientific notation typically, this one is, and we're going to turn it into standard notation. So my number, again, I'll write it larger to start with. Starts out looking like this. Is this a small or a large number? Small. How do you know? It's a negative exponent. Now, in its current form, it's neither, right? It's 3.2. It's a single, it's a one number before the decimal, potentially one or more numbers after the decimal. But when we talk about this one being a small number, it means that I'm going to change it into something smaller, correct? That's what that means. So which direction, looking at this number, does the decimal have to go if it's going to be smaller? Yeah, it's going to go that way, correct? Got to move it to the left. It's my right from where I'm standing, but it's your left, yeah? I think, yeah, okay. Cool. So we need to be able to move it, and the way it's currently written, I really can only move it one time before I run out of space in which to move it to. And so I need some more leading zeros that allow me to move spaces over. So I'm just going to put in quite a few zeros, intentionally more than necessary for the particular moment I'm working in, okay? And I've moved it once, twice, 3, 4, and 5 times. So I did not need the very first leading zero. You're welcome to either include or to not include the next zero. That's fine either way. That's an optional. I'm going to leave it there. But I have a 0, and then I have my decimal point where it ended. Then there are 4 zeros and a 3, 2. This is a very small number now, right? Almost 0. Okay, are we good? Okay. So our next example is still scientific notation. Notice on this one, the numbers themselves are being multiplied. Now, we've talked about multiplication being commutative and associative. Do you remember what those words meant? Well, we did it back in chapter 6. We haven't done it in chapter 7 yet. Commutative means you can do it in either order, right? So like 3 times 5 is 5 times 3. And associative means you can regroup things. So I can have the grouping like it is right now around the first 2 values and around the second 2 values, but I could also regroup things and I could put them around the middle 2 values or something like that. If I put both of those properties at play here, what it allows me to do, because everything is multiplication, is regroup this and commute this so that the pieces that are like one another are next to one another. Right? So the pieces that are before the times 10s, the 6 and the 8, can be multiplied by one another, and the 10s with powers can be multiplied by one another. So let's start with the beginning. What is 8 times 6? 48. Now, I don't know about you, I don't want to write down 10 to the 12th with a bunch of zeros. And I don't want to write down 10 to the 15th with a bunch of zeros. And we learned some properties, again, back in chapter 6. Again, you've learned them before, but you were reminded of them. How can I combine these 2 pieces together? You add them. Then what? You add the exponents. So I'm going to dot here. This is 10. What will my new exponent be? 27. Okay, is that good? Now, at this point in a particular problem, I might be done. Am I done in this problem? No, what's wrong? I mean, I did the pieces that were alike. Is my final answer, the answer I currently have on the board, in scientific notation? It is not. What's wrong? It's close. What's wrong? 48 is larger than 10. That's exactly right, Abby. So as I'm taking a look at this 48 needs to have a decimal somewhere. Where? Yeah, it needs to be right here, right? This is where it should be. Now, I can't just put the 4.8 in here without sort of accommodating for the change that I've made. Did I have an originally large number, 48, or small number? It was too large. Now, if I had divided these, I might have ended up with something that was too small. True? I could have, right? If the number had been 8 over 6 or 6 over 8, I might have potentially ended up with something too small to actually have it in scientific notation. This one's too big. So when I made the 4.8 out of the 48, it started out originally large. I have to accommodate by increasing the value of the exponent. So my actual value here, I don't like the fact that I've got decimals and the multiplication signs. Let me put that in parentheses to clarify. This 10 will now have a power of 28 because the original number was large. So the exponent now needs to be larger. Right? I adjusted one of them to be smaller, so I have to adjust the other one to be larger. Feel free, if you wish, you can also write this with multiplication symbol like that. That will work because we're not dealing with algebra X's right now. That will be fine too. Okay, you ready to shift to another topic pertinent to operations on decimals? Okay, we're going to take a look at rounding. Specifically, well, more generally estimation, but a lot of it's rounding. So the first one is rounding to the nearest blank. That blank is because we get to round to the nearest lots of things. You could round to the nearest hundredths place. You could round to the nearest 10,000ths place. You could round to the nearest thousands place as well, right? It doesn't even have to be decimals. But when we're rounding, we're going to find the location that we're supposed to round to. 0 to 4 means we round down, and 5 to 9 means we round up. Now that's different than the second one here. The second one here is called front-end estimation. It's still an estimation technique. There's still some rounding involved, but it doesn't work the same way. With front-end estimation, you use the first value or the first couple of values. It's a little fuzzy on the problems, and you usually get to make a decision. And you round off. Rounding off is actually the same thing, if you will, as rounding down. But notice there's no conditions. It doesn't say if the number does this, you do it. You just round it off. In other words, everything after that digit zeroes out. Okay, that's front-end estimation. So let's do a couple of examples of these different types. The first one is just specifically rounding. So it wants us to round as specified. Our number is 203 and 651 thousandths. So the first one says to round to the nearest hundred. And each time I'm going to do this, I'm going to rewrite it in the space that I have so that we can identify what place value we're supposed to be rounding to. So if this says nearest hundred, what number is in the hundreds place? The 2. Okay, 100, no TH, is in front of the decimal. This is the number 2 that I'm going to be working with. The 2 will either stay a 2 or become a 3. Those are the only options. And everything else is going to become zeros. We look at the next value over to make that decision. That value is a 0. So over here it says, found the location around 2, we did that. 0 to 4, we round down. Now, rounding down does not mean the 2 becomes a 1. It means that everything after that becomes a 0, so that the value itself is lower than it was before. This original value is 203 and some change, right? Yeah? I don't have a 0 on the end. Why do I have a 0 on the end? There's a 1 on the end of that. Oops. There we go. The black going on. Okay. So everything else will zero itself out. It won't actually be there. So the whole number itself is going to be smaller than it was before, but that doesn't mean the 2 is going to be smaller. Okay, the number we're rounding to cannot change unless it goes up. So this number, will it go down or will it go up? It's going to be lower than it was before because this number 0 is between 0 and 4. So this will become 2, stay the same at the beginning, and everything else will zero out. If you just write it as 200, that's okay. But I want to be really clear that everything is still sort of there, but it's all in 0 form now, at least for our notes. The next one says nearest hundredth, 203. We'll get it written right this time, 651. All right, hundredths place. What number is in the hundredths place? That's the 5. Okay, is everybody good with that? And we will go 1 to the right to decide whether we're going to go up or down. Now, everything before the 5 stays the same. And the 5 will either stay a 5 or become a 6. And everything after the 5 will be a 0. The only decision we have to make is what the 5 does. Will the 5 stay a 5 or will it become a 6? It's going to stay a 5. So the 203 and the first 6 after the decimal place, the 6/10, stay the same. The 5 we just discovered will also stay the same. And the one after it will become a 0. Again, if you choose just to leave the 0 off, that's not a problem for what we're working with. That's okay. One more time, one more place to round to. It says the nearest units place. What number is in the units place? That's the 3. And they can use the word units or they can use the word ones. That's fine. And we're looking to the right of it, the 6. So the numbers before the 3, the 2, and the 0 will for sure stay the same. Is the 3 going to stay a 3 or become a 4? It will become a 4 because the number after it, the 6, is between 5 and 9. And everything else after it, again, you could leave them off if you wish, or you can write them out as zeros. And the wish part is the ones that are after the decimal place that you have a choice on. Okay, let me show you the difference then in rounding and front-end estimation. And then we will table our last example for next time so we have time for the group work. So the directions say we're going to use A, rounding, and B, front-end estimation to do the following. And I would like for you to notice that they don't tell you what place value to do anything to. I don't love that, but that is what your book's going to do on this particular problem, so I want you to see it right now, that they're going to do that. But what that means is that you get to pick. That's kind of nice, right? We get to choose. So don't choose something that keeps lots of decimals, but make a choice that seems reasonable. For example, it is reasonable on this problem to either say we're going to do it to the tens place or the units place. Okay, so I'm going to let you pick. Do you want to do it to the tens place or the units place? Units. Okay, we're going to do units then. So if I'm working with units, A says rounding, and we're rounding to the units place by our choice. Okay, we had a choice in the matter. So the 89, the 9 is what I'm rounding. The 4 tells me what I do with it. What am I going to do with 89.47? It will become 89. And I'm going to leave off the decimals at the end as I'm doing this problem because it's got some calculation. The next one's a 2, and I look at the 1 over here. So the 2, looking over at the 1, will it stay at 32 or will it become a 33? It'll stay at 32. And if I subtract this, it's a really nice one, it becomes 57. Is that okay? Okay, so what would it actually look like to say I'm doing front-end estimation? Well, because y'all chose units place, you're not going to get to see the fun of it. So I'll show you the tens place here in just a second. But what it means is that it doesn't matter what comes after. They get ignored. I don't care if it's a 1, I don't care if it's a 2, I don't care if it's a 9. I ignore it. Now on this problem, what happens is I still get the 89 and the 32 that we had from rounding the way we rounded before. It didn't change anything. It doesn't look like it's any different. But check out what happens if I do this with the tens place. Here we go. If I do this with the tens place and I do rounding, the first one would be a 90 and the second one would be a 32. Agreed? If I were rounding? Is everybody okay with that? But if we're doing this with the tens place with front-end estimation, that 89 is an 80 now. Because I keep the tens place and I zero everything out. Doesn't matter how close it is to 90. I keep the number, zero everything out. And the same thing for the other one. I keep the number, zero everything out. That should have been a 30, not a 32. You know what? Just do this. So when I subtract, this first one would have been 60, whereas the last one would have been 50. Okay, so front-end estimation has less accuracy in general, but sometimes it works out that it's pretty close, if not exactly the same. Depends on the unit you're working with and the numbers that you're given. Now, Part C actually says we're supposed to, well, it doesn't say Part C, but it's sort of inherent in the way it's described. Then perform the actual computation to see how close your estimations are. So we're going to actually do it with the numbers given and subtract. So 7 minus 6 is 1. Thank you. How about 4 minus 1? 3. 9 minus 2? 7. 8 minus 3? 5. So our 5731, which is our actual value, is really close to what we got, obviously, with either of the two methods when we did the units place. And if we're looking at tens place, which I did at the top, it was actually pretty close to the rounded one, but it's not very close at all, really, I mean, comparatively to the front-end estimation one. Front-end estimation generally is a less accurate estimation method, but it is quicker, it is simpler.